All right, good evening. Welcome to the second workshop here at UC San Diego in the Envision Maker Studio. I'm glad to be here. Thank you for being here as well. Those in person and those on YouTube, hi. If you like this, give us a like, give us a share, and we'll get more people interested in computational fluid dynamics. So, this topic is traditionally seen in grad schools, but more and more undergrads are using these tools on student teams like race car, but also for research and the internships as well. So it's a really valuable skill for you to learn. First, a very quick thank you to the Envision Maker Studio. We're here in a really cool space. On YouTube, we don't really have a shot of that, but it's an amazing environment for the students to learn here. Lots of equipment for 3D printing, but also laptops, so we can host this kind of thing here. It's also a big thank you to the IT services and AV services for your support. So, what are you going to learn today? Right? We all came to learn something. So these are the promises we're making. By the end of today, you're going to understand these 4 things. Simulation is leveraged throughout every industry. We're focusing on computational fluid mechanics today, but you'll see that there's a lot of other applications for simulation. Learning simulation in school is very attainable. It's straightforward. We're going to show you the resources, how to do it. You already took the first step, but there's so much more that we can cover in 2 hours. We'll also get into the basics of CFD theory, and then we're going to wrap up with a practical application using Ansys Fluent. And finally, we'll show you that knowing how to innovate with simulation is a really powerful tool to launch early career engineers. Just really boost your career. It looks great on your resume. So, we're on the workshop number 2. If you're interested in this stuff, we have mechanical on Monday, right? So we're doing structural analysis and FEA, as well as optimization. And on Thursday of next week, we are doing simulation for autonomous vehicles. And then we'll wrap up. And if you missed Tuesday's workshop, please check it out. It's on the same YouTube channel you're watching now on Ansys Tech Tips. So, this is some results just from our biggest customer and some of our most innovative customers have given us feedback showing eventually everyone's going to need to learn simulation in some way. Maybe they're not analysts, but they need to understand what the basics are, right?
Team New Zealand's the longest established brand in the America's Cup, the premier marquee event in sailing. Every competition we've entered, we've either been a Louis Vuitton finalist, won the Louis Vuitton, or on 2 occasions won the America's Cup. My involvement with the America's Cup and the design side goes back around 16 years. And in that time, we've seen the transition from physical testing, where almost everything we did was done in the wind tunnel or the towing tank, through to, in this cup cycle, we've finally managed to get to 100% numerical analysis and sort of digital prototyping. And the productivity gains and the extra insight that's offering us is extremely valuable. These boats are probably 30 to 40% faster than we originally entertained, and so continuously through the development of the boat we've had to update our models.
We chose to use Ansys because it's a market leader. Really, it's it's an easy software to use quickly. It's easy to get good, reliable, quick answers. And from an aerodynamic perspective, the really key technical thing we're looking for is good turbulence modelling, and that's really where Ansys, I think, is miles ahead of other CFD codes.
The centre of how we design the boat is a program called the Velocity Prediction Program, or VPP, which is a solver that combines the physics of the hydrodynamics with the aerodynamics, and is a tool really we use to work out how the boat's been sailed.
In the past, we've really struggled to run enough design points, to get enough information into the VPP, and this time round, just with the ease of being able to simulate a lot of different design points, really automation, I guess, has probably been the key thing there.
with Ansys, we've modelled the aerodynamics of the yacht in its entirety and through a massive range of situations, which we really call an aero matrix, which involves up to sort of 750 different simulations per design of the wing and sails. That matrix gets fed into the VPP, which then finds an equilibrium between that and the hydrodynamics, and predicts how fast the boat will go, what are the optimal angles, different settings, different trims for the wing. So the CFD software is absolutely key for us to understand the boat. One thing we've really developed since we've been sailing the boat is how we trim the wing. Which has really been a continuous process between getting feedback from the guys on the water, what feels good, the data that we get from the water, what is seen as being fast, and then comparing that to how we're setting up the models in the CFD.
If we weren't using Ansys, I think we would have struggled to improve our aerodynamic package. And I think we would have been, it's more that you would struggle to be confident.
I don't think we could have got where we are without Ansys. It really has been the cornerstone of our design process and is a key contributor to where we are now.
Ansys products absolutely help us be competitive.
Nice. I hope you guys found that interesting. Just a little example of what you can do with CFD that you might not expect, right? You kind of see it in high tech. You may see it with big companies, but maybe you didn't think about it for racing. But Ansys, we sponsor a lot of racing teams. Ferrari, and this team as well from the America's Cup. So, where is simulation used? Well, it's used throughout the entire life cycle of a product. Of course, it's used in design and in ideation, right? When you just have that idea. But more than that, it's used in the product. It's used, in the Internet of Things. The Internet of Things is playing a huge role in our future. Simulation is really finding a useful thing to do with that data, right? So just keep it in mind that today we're focusing on the design, but there's so much more that you can do with it. So yeah, we're used in literally every industry. You can take a look on the board and see the customers who've agreed to let us talk about their work. I mean, there's all kinds of applications for CFD. Like you wouldn't expect them, right? Like necessarily Speedo or Dyson, right? Like, oh, it's household appliances. It's stuff I use every day, especially Speedo, if that's the weird one, right? But they use us for hydrodynamics and optimization. Athletes love simulation; it helps them get the edge, even in bike racing. So again, today we're focusing on fluids. Ansys, we're a multi-physics company. We do everything from FEA, fluid mechanics, solid mechanics, electronics, semiconductor, mission critical embedded software, everything you can think of. And we acquire companies on a regular basis that have interesting technology that we think is going to be useful for our customers. So including additive manufacturing simulation, that's a new one, optical simulation as well. So keep your eye out for academic stuff for these new topics. While I have the ear of a lot of students, I want to give a shout out to our design teams. We sponsor hundreds of them worldwide, and we always welcome new applications. So if you have a design team like race car, Hyperloop, Rocket, get in touch with us. We'd love to sponsor you. And, that includes the training, software, mentoring, support. Just get in contact with us. We'd love to help you. And it turns out that when you do simulation, you end up winning more of the time. And companies are looking to hire students with that skill set. So please just consider that. And these are just some examples of recent publications talking about, hey, we really don't hire the traditional students anymore. We like the students who build things and who do simulation. So if you want to learn Ansys, check out YouTube. There's a ton of tutorials there from us and also our partner companies. So if you just hashtag Learn Ansys on YouTube, you'll find a ton of content. So we also have developed an open source class with Cornell University. You can take this 100% for free online, and it covers the practical application and theory of CFD and FEA. It's actually how I learned simulation when I was in school, and I can tell you, it's not marketing fluff. It's incredibly useful. Please check it out. That's after today, this is the #1 resource for you guys if you decide to move forward and do more with Ansys. If you have a question, you get stuck on anything, we've created a student community for you. You can post questions here, you can find resources here, and connect with students around the world. And even more than that, we have our engineers on this community on a daily basis answering your questions. So you'll get an answer, and as long as you can explain your question with some screenshots and some descriptions, this is the right place for you. So how do you access Ansys? Well, if you happen to go to UC San Diego, you have it, right? Check out your website. But if you don't, right, and if you go talk to your professor, go talk to your IT, see if you already have Ansys. If you don't, get your student team sponsored. If you're not part of a student team, go to ansys.com/student. We have a student version, which is the same products that we offer at the commercial and academic level. They just have a node limitation. So check that out. And you can always click contact us at ansys.com/student. If you have a need for Ansys, you're interested in it, please let us know what you want and why you want it. We'll do our absolute best to get the tool in your hands. Here's my contact information. Blasting it out on public, so please give me a shout if you need anything. I don't answer technical questions. If you have one of those, go to the student community. But anything else, feel free to reach out to me. So at this point, I want to introduce my colleague. He has a PhD in mechanical engineering. Specifically, his background is in fluid mechanics and computational fluid methods. So this is Dr. Zoran Dragolovich, and I couldn't be happier to introduce him. He's got years of experience at Ansys. This is the fun part, you guys. We get into the meat of today. So thank you for your time and enjoy.
All right. Thank you, Jacob. Can you guys hear me okay? Well, thank you very much for attending our session. My name is Zoran Dragolovich. I'm an application engineer with Ansys. And today, I will talk about CFD. At Ansys, I support Ansys CFD tools and the associated workflows, and today we will have a brief session just to introduce the CFD, explain what it is, how it works, and show some interesting CFD applications throughout different industries. Then I'm especially excited to tell you about the new Fluent experience that has been brought by the Ansys development team in the version 19.2. You can set up, solve, and post-process your problem in a single graphic user interface in Fluent, starting from importing the geometry, creating the surface mesh, generating the volume mesh in the brand new Mosaic Technology, and I'll explain what that is, and then setting up and solving the problem without having to use different applications, save the files, read them again, and so on and so forth that our users had to do in the past. So we'll talk about the Mosaic technology, explain what it is, and then we'll talk about the additional enhancements that have been introduced in the recent version of Ansys. Let's start with the essentials. So before I talk about CFD, I'll mention a few words about fluid dynamics in general. As you know, fluid dynamics is the science of fluid flow analysis, and it can be treated or it can be studied in several different ways. Typically, people do theoretical fluid dynamics, experimental, and numerical. Computational fluid dynamics is the numerical portion of the fluid dynamics field. Essentially, it consists of solving the conservation equations of fluid flow, heat and mass transfer, and the flow of the associated phenomena as a numerical problem. So you take the conservation equations that calculate how the conservation of mass, momentum, and energy is done. These are partial differential equations which are solved numerically in a computer. CFD can provide the very detailed information about the fluid flow behavior. It is used at all of the different engineering stages of the analysis, including the conceptual studies, detailed product development, optimization, troubleshooting, and redesign. I'd like to point out that CFD can never completely replace the experimentation, the experimental data, and the basic science, but it can complement both experimentation and theory. Essentially, CFD can, once validated, CFD can completely replace the expensive test equipment and aid either in planning new products or troubleshooting and redesigning the existing products. How does CFD work? Well, theoretical fluid mechanics is based on solving the partial differential equations. These equations describe how mass, momentum, energy, and species concentration is preserved or conserved during the fluid flow analysis. What happens in the background when you solve CFD is that the partial differential equations are discretized into a nonlinear system of algebraic equations, and at the same time, the space where we are looking at the fluid flow is broken or split into small control volumes. An example is this pipe that is shown on the right-hand side, which is divided into cells or control volumes. This discretized domain is called mesh. What we are doing here is we are solving for the field problem at the cell centers. So we take each of these little cells and we solve the algebraic equations that are generated from the partial differential equations that describe the conservation of mass, momentum, and energy. And then we are solving this as a system simultaneously on each and every cell, which produces the result in form of the field, which is discretized at the cell centers. Ansys Fluent is a commercial CFD solver which is both versatile and accurate to tackle a lot of different complex physical problems from the industry, starting from the pressure drop and velocity around different objects exposed to the external flow, such as gas turbines or airplanes or automobiles, high lift and drag solution needed to resolve the internal flow instead of pipes or various different internal structure, resist wind loading while minimizing the cost of different objects that are exposed to the wind. So basically the goal here is to optimize the shape of the object to minimize the drag, and so on and so forth. CFD is rarely used as a standalone tool. As a standalone tool, you can solve one single problem that only looks at the fluid flow and the associated heat or mass transfer. In most situations, CFD is used with other tools. In this particular example, we are using the conjugate heat transfer analysis with mass transfer in order to solve the problem of defrosting. As you use the vehicle in the winter conditions, there's a thin layer of ice that forms on the windshield. The task of the CFD analysis in this particular case is to solve for the fluid flow of hot air from the defroster on the car, and then calculate how quickly this layer of ice is going to melt under the given temperature field. So we want to find a very accurate result, very accurate solution of the heat transfer distribution across the windshield, and also how quickly the ice is going to melt. This will give us the idea about the performance about one single design. But what if we want to optimize this design? Obviously, this single analysis is not going to tell us much. It will give us a good insight. It will maybe hint at what needs to be done next, but it will not give us this whole picture. In order to be able to optimize this design, we need to use optimization tools that are coupled with CFD analysis. In this particular case, we are using Design Explorer, which is an optimization tool based on parametric analysis that resides in Ansys Workbench and can be coupled with Fluent and additional tools. So this is an example of how you would use CFD in a realm of the coupled analysis, where you use other solvers in order to solve the problem that you're facing. As a result of this analysis, we see the optimized shape of this defroster in the lower right corner. Now, there are other forms of coupling that you may consider. Engineers typically look at the very complex physical systems. You may have fluid flow, but you may have other physics that could dominate. For example, in an electric motor, what is important besides the fluid flow is the propagation and conservation of the electromagnetic field, and the behavior of the structure that electric motor is comprised of is important as well. In this particular case, the electromagnetic field that is generated in the coils of the electric motor gets dissipated. It generates the heat. This heat can significantly change how the conductors behave. It will change the electrical conductivity. And it can also significantly contribute to the fatigue and durability of the solid materials that comprise the electric motor. In order to solve this problem completely, we need to couple the fluid dynamics with the electromagnetics and structural mechanics. So in this particular case, we use Ansys Maxwell in order to calculate the generation of the electromagnetic field and its dissipation into the heat inside the coils. We use Fluent in order to solve for the flow of the coolant. We need to cool this motor in order to make sure that the temperature in the coils, which are sensitive, will remain at the design value. And we also need to use mechanical in order to find the amount of thermal stress and other dynamic stresses and how they change in time in order to predict the behavior of this electric motor. So that is an example of how CFD can be used coupled with other physical solvers in order to give us a good picture of what's going on in the device of interest. Let's take a look at a couple of selected applications just to give you the idea. So CFD can be used to solve physically large problems. You could look at spaces such as building atriums and lobbies. And in this particular case, we want to see how the smoke propagates. As you know, this is a very important problem when you design the building. The pathways of the smoke propagation can help us design the HVAC system. They can help us design the sprinklers and their placement. And they can also help us decide on how we can separate or segment these atrium in order to minimize the smoke flow and kind of localize it to the area of the building where the fire started. In this particular case, if you look at this railing, you can see how the smoke plume adheres to the railing, which is driven by Quanda effect. And this realistic smoke propagation was rendered in Ansys CFD post by using the volume rendering, which essentially turns on the black and white color map and maps it to the concentration of the smoke particles in the space of the atrium. How does smoke affect your lungs? That's an entirely different field. So in this particular case, we have the lungs that were based on the 3D scan of a real patient. And as you observe the details of the particle propagations to the lungs, you can see that the lungs themselves expand and shrink as well with the breathing of the patient. So this is made possible by coupling the CFD analysis with the mechanical analysis, which determine how these tissues are going to expand and shrink. And as I mentioned, we can use the real data based on the scans of the internal organ of the patient. Then another interesting application, since we are in the realm of medicine, we can study the blood flow in the arteries that are affected by the aortic aneurysm, which is the abnormal expansion of the artery in the region near the heart. By studying the blood flow, we can see how this aneurysm impacts the flow and how this flow obstruction can contribute to the expansion of the aneurysm and further worsening of the problem. We can also plan the insertion of the special stents that will help alleviate the problem as well. And in that particular moment when we have the stent, which is elastic and made of solid materials, we have a fluid structure interaction between the artery tissue, the stent, and the blood flow. Somebody also mentioned about biomechanics. And this is a perfect example where CFD is used in the biomechanics. This is an artificial heart. And we have these tiny leaflets which are placed in order to control the blood flow through the heart. So if we observe the flow, we can monitor the entire cycle that corresponds to one single heartbeat. What happens in this particular case is that the pressure field at the surface of these leaflets is transferred from CFD as a CFD solution onto mechanical. In Ansys mechanical, this pressure field is used as a time-dependent load. Based on this time-dependent load, mechanical calculates the stress and motion of the leaflets. Once it calculates the stress and motion, the displacements of each leaflet are propagated back from mechanical to Fluent. Fluent then deforms the mesh based on the leaflet displacements and then continues calculating the field until the solution converges. And this happens over again at every time step. So you could have a very high fidelity solution of the flow field, and as well you can watch this solution interact with the mechanical solution that shows you how these leaflets deform at the pressure of the blood flow. Another interesting example is comprised of particle flow in a concrete transport truck. So we can look at the concrete particles and how they move inside this large truck that serves the purpose of mixing the different concrete ingredients together. You can use this solution to optimize the process and come up with the conditions that are required to produce a good quality uniform concrete properties. This, again, is an example of how you can solve the problem in a relatively large space and relatively small space. You can look at the particle propagation in the ducts and their impact on the filter, which is simulated as a porous material. So you can see how the particle propagation through the filter is going to obstruct the flow and impact the velocity and pressure in this area. Then again, a large and a small problem, but a slightly different physics. Here on the left, we have the simulation of the interface between the ocean, water, and air. This type of simulation is solved in Fluent by using the volume of fluid method. Volume of fluid method has the surface tracking capability and is typically used to simulate situations where you have either a single fluid and a single gas with an interface between them, or the mixture of fluids and the mixture of gases, also separated by the interface. So in this case, we have the response of the structure to this single rogue wave. On the right, we have the similar problem, but an entirely different space that we observe and an entirely different objective. We have a vehicle that is being processed in a vehicle plant. There is a process which is called e-coating that serves the purpose to deposit a layer of paint by using the electrolysis. So in this case, the vehicle is being dipped into a pool that contains the electrolytic liquid. So if we do that, what we are typically looking for is to make sure that we don't have any air gaps inside the vehicle as it's submerged, because these air gaps are going to adhere to the vehicle's surface and they will prevent the uniform deposition of paint. Also, as the vehicle emerges from this liquid pool, you want to make sure that there are no small pools of paint accumulated. You want to make sure that the drainage of the vehicle is complete. So we have the same type of numerical approach used to two entirely different processes. Then we have some interesting periodic flows here. In the case of the left, we have an airflow around an axial wind turbine. And if you observe the wake behind the turbine, you can see some interesting structures which are vortices that occur due to the vortex shedding behind the trailing edges of these blades that comprise the turbine. On the right-hand side, we have a different type of periodic flow that occurs in the internal combustion engine. So this is a full conjugate heat transfer problem with chemical reactions in order to simulate the burn of the gasoline and how that impacts the motion of the piston. If you look at the motion, you can see that on the right-hand side, we have the maximum temperature in the domain as a function of the crank angle. So you can observe how exactly the temperature changes as the crank angle advances in value. We also study external flows a lot. In automotive industry, it is paramount to find out what the external flow looks like in order to improve the automotive design. Improving the drag and lift can drastically reduce the cost of fuel, especially nowadays when more and more companies are building their electric vehicles. You can see that the automotive, the airflow around a vehicle creates a rich turbulent structure, which is resolved by using scale resolving methods, such as LES, and hybrids, such as SPES and DDS. So these hybrids essentially use the highly accurate scale resolving method in the wake of the turbulent region, while the RANS method, which is computationally less expensive, is used in the boundary layers, since the turbulence in the boundary layers is not as intense. The automotive makers also worry about the noise that the passengers would hear inside the cabin. From that point of view, there are special regions of interest, such as the turbulent wake behind this side mirror. This turbulent wake generates the turbulence-induced noise, which then creates the pressure field, the periodic pressure field at the side window of the cabin. This pressure field, in turn, generates the vibration of the side window, and these vibrations are propagating into the cabin, and they reach the passengers' ears that way. So we want to find out how we can optimize the shape of the mirror in order to minimize the noise. The field that studies the amount of noise generated by turbulent flow is called aeroacoustics. And in this particular case, since we need to resolve the vibrations of the side window, we need to also consult the field that has to do with the vibration, with the noise driven by the solid vibrations. We obviously have to solve this as a coupled problem, where we use Fluent in order to solve for aeroacoustics. We derive the noise from this turbulent flow, and then we use Ansys Mechanical in order to solve for the vibroacoustics inside the side window and inside the cabin. And we coupled these two applications through the workbench. So these are some of the typical examples of how people use CFD in industry and how CFD can be coupled with other physics solvers in order to provide the complete picture, either to tell you something about the optimal design or to tell you something about situations where you have multiple physics involved, like the electric motor that I showed earlier. Let's talk about the new Fluent experience, which enables us to solve the entire problem, starting from importing the CAD geometry through meshing, through setting up the problem, solving and processing in one single window. So import of the geometry happens seamlessly. You would take the geometry either from SpaceClaim or from other CAD tool, generate the surface mesh inside the Fluent interface, extract the region of interest. You would generate the capping faces at the locations that you specify, and I will show in a demo how that occurs. Generate the high quality volume mesh, set up and solve the problem, and finally post-process while being in the same graphic user interface and while using the data that while they're still in the memory of the solver. This watertight task-based workflow is really, it relies on the existence of the clean CAD. What does that mean? That means that the surfaces that are adjacent to each other need to be completely tightly connected. So we cannot have any gaps that would let the fluid flow through. And we cannot have any openings. So the surfaces also have to be completely continuous. Other than that, you could have as complex geometry as you like. There are no limitations in how complex the geometry can be. You could have large length scales, different curvatures, high space counts. Any of the types of geometries that they showed in examples can be featured in your model. The only requirement is, for now, that your CAD is watertight, and in the next release of Fluent, we will have workflows that also admit non-watertight geometries. Typically, if you have a very dirty geometry with different gaps that are inherited from the CAD, you can use the wrapper to handle that. We are talking about the task-based workflow, the brand new tab that exists in Fluent 19.2. We still have the original classical workflow that experienced Fluent users are familiar with, and it still has the sophisticated feature that allows them to extract the geometry from arbitrary CAD models. Let's talk about the speed and efficiency. So when they compare the new workflow with the existing classic workflow in Fluent, Fluent meshing experts find that the new workflow is about 70% faster and requires about 50% less hand-on time while producing the comparable or better type of mesh. Another concern, once we have the mesh developed, another concern is the accuracy and the solution time. They are always highly dependent on the mesh type and quality in CFD. Hex core elements are known to be very efficient. You could easily fill the space with the hex core. They fill the volume very well, and they optimally solve the problem in many cases where the flow is aligned with the mesh. That minimizes the second order error or numerical diffusivity. Tetrahedral elements, on the other hand, are far less efficient than hex core, but they are necessary because they easily fill the volume in case of the very complex geometry. And then polyhedral elements are somewhere in between. They are much more efficient than tetrahedrons and somewhat less efficient than hex core, but they also fill the geometry that has challenging curvatures or challenging length scales very well. So in the classical approach, before the Mosaic Meshing method was introduced, it was always a challenge to choose the best meshing method. Very often we had to compromise. We had to use tet elements in the very challenging regions of the geometry, or polyhedral elements, and we would prefer to use hex element everywhere else, where the geometry is not a limitation. And then we would have to somehow transition in between. In most of the cases, we would either need to sacrifice the accuracy or the quality. We would have to generate the non-conformal mesh, or we would sacrifice the quality in the conformal meshes that are stitched together from different types of elements. In order to overcome this problem, Ansys has patented the new Mosaic technology, which uses polyhedral prisms to very nicely fill the area next to the wall where the boundary layer is located. These are the high quality cells and highly efficient cells as well. You need to, you're required to use significantly fewer cells in this case compared to the triangular prisms that are otherwise required with tetrahedrons. Then the rest of the space is filled with hex core, far away from the boundary layers and far away from the walls, which is characterized by the high quality and the fast solution time. The glue between the hex cores elements and the prism elements is the poly elements, which conformally connect these two regions. Here is an example of the mosaic meshing in action. So we are looking at the detail of the mesh where the geometry is moderately complex. We see that we have a large amount of space that is filled with hexes in fluent meshing, which, as I mentioned earlier, is a more efficient way of solving the CFD problem compared to tetrahedrons or polyhedra. Then we also have polyhedra and prisms in the near wall regions. And we see that even in the regions where the angles are fairly sharp, we have a very smooth transition and the good quality elements. So this is what I wanted to bring your attention to, the new Mosaic technology. We will see this technology in action and how it can be used to solve a problem. Another novelty in the version 19.2 are the expressions in Fluent. If you guys have used Fluent before, you may know that if you had time-dependent boundary conditions or the boundary conditions that depend on the space, on X, Y, and Z, you had to write a small C code, which was called UDF. This is not a big deal. Usually most of these codes were not extensive or not too demanding. You needed to know a little bit of C. You needed to convert the units where needed by yourself. And you also needed to know the macros that tell the C code how to interact with the Fluent solver data structures. Right now, that need does not exist anymore since we have the new expressions in the version 19.2. When you turn on, this comes as a beta feature for now, and as we advance into the further versions of Fluent, this expression capability is going to advance from being able to apply different boundary conditions to being able to apply different material properties using expression actively in the conservation equations being solved as source terms and so on and so forth. When you turn the beta features on and when you turn the expressions on, you will see this button f of x. So you can scroll down, click on the button, select expressions, and then type your expression in the expression editor. For those of you who use CFX or CFD Post, you're familiar with the CEL language that is used for the expression over there, and you will find a lot of familiarity between the new Fluent expressions and what you are used to in these other tools. So you could save these expressions in your notes and then just copy and paste. They need to be consistent as far as the units are concerned. So if your expression describes the velocity, then obviously the units have to be meters per second and so on and so forth. You can directly type the expression in the boundary condition, or you can generate the named expressions which can be then reused at different places. So all you have to do in that case is to type the expression name right here, and you'll be able to use it. Here's an example of using an expression in a pipe flow. So if you solve this problem with the T-junction, with the constant velocity at the inlet, you can see that the flow is not fully developed. So your solution is not completely realistic. The flow is still developing as the fluid advances from the inlet to the outlet. In order to overcome this without the expression, you would have to probably extrude this inlet further upstream and give the flow enough space in order to fully develop by the time it gets to this junction area, which is of interest. Or again, use a small C code or use a spreadsheet in order to apply the profile at the inlet. On the right-hand side, we have the same case with a single expression that specifies the parabolic flow profile. We can see that the flow is developed as it comes to the T-junction region, and it is as such much more accurate. There are a couple of other exciting innovations that occur in the last two releases of Ansys. We have Puma, which is the algorithm that allows you to refine the mesh in polyhedrons by marking these cells based on some criterion, such as the density difference across the free surface or pressure difference. So you essentially refine the mesh on the fly This was only possible with tetrahedral elements, and now it's possible with polys as well. You can see how efficiently you can solve this problem with sloshing, where the liquid surface breaks into various complicated structures, including the droplets. So this can only efficiently be solved if you have the mesh refinement that follows the solution on the fly. We can also use Puma in order to resolve for the shockwave structure distribution in real time, flame front capture, and other areas where you have a tiny interface that needs to be resolved correctly in order to accurately solve the problem. Another detail that I'd like to bring your attention to is the overset mesh. This is an example of a simulation of a robot where the geometry sometimes needs to be modified by replacing components based on the design requirements. Imagine if you wanted to replace just the front of this hand of the robot. If you were using dynamic mesh without overset, you would probably have to start from scratch. You would have to go back, change the CAD, discretize the mesh again, generate the brand new mesh, that is, set up and solve the problem, and only then have the solution that you need. With the overset mesh, it has components that follow the individual parts. You can see that each individual part is meshed in the separate component, and then this is imposed onto the uniform background mesh. So if you were to just take this front portion of the robot and replace it, all you have to do is take away that component, generate the new geometry in that area only, put the component back, and continue solving. So you immediately have a new solution, even though your geometry is completely modified at some region. And finally, I'd like to also mention the new visualization client capability in Fluent. This allows people who use cloud a lot, or clusters, to visualize their batch runs. As you know, if you run a batch model with Fluent, it is very difficult and almost impossible to observe the residuals during the run. You could print out the variables that you monitor, but you cannot vividly observe them as in a graphic user interface. It is also much more difficult to plot the contours and various different post-processing, generate various different post-processing objects that you would normally do. With the visualization client, all that you need to do is print out a little text file once you're done preparing the model to run, or insert the flag that will require the solver to print out this flag during the batch process. Then read the text file in, which will tell Fluent client where the solver is running. Fluent will then connect to the solver, bring this interface that will allow you to monitor residuals, plot the solution on the fly, observe the console output from the solver, and use various text user interface commands in order to change the conditions. You could change solver settings, or you can change boundary conditions during the run in real time, and stuff of that nature. So let's just exit the presentation to demonstrate this new workflow. So we will solve the problem of fluid flow inside an elbow. And this is a mixing elbow where we are looking at the inlets of the fluid through two different openings. And we will solve this as a heat transfer problem in order to find out how well the fluid mixes inside this space. So I will generate the geometry from scratch and then import it in Fluent, and then do the complete pre-processing in Fluent graphic user interface. I will only use SpaceClaim to generate the geometry. SpaceClaim is our pre-processing tool, and it is considered a CAE tool. It can be used to prepare geometries for different types of analysis, including CFD, mechanical, electromagnetic, and so on and so forth. To open SpaceClaim, you can navigate to the directory where Ansys is stored, your installation, and then just navigate to SpaceClaim. What I do in Windows 10 is I just type ACDM, and I type the version number, and Windows 10 will bring it up. So now that I'm in the GUI, I will start by generating the sketch. SpaceClaim has 3 different modes: sketching mode, cross-section mode, and the full 3D mode. I'll have the sketching mode on, and I'll start by creating a circle. I want to create a pipe that has 100 millimeters in the diameter. So I can click at the center of the coordinate system. I can click on the circle icon here, and then I move the mouse in order to increase the radius of the circle. A very easy way to specify the diameter is to just press the spacebar as I do this. That freezes the operation, and then I can just type 100 millimeters. So that completes this simple sketch. Now, in order to make sure that I have millimeters on, and they are needed in order to import this geometry into Fluent, since the meshing is handled on the millimeter length scale, I need to turn on the SpaceClaim options, and then select the units and specify that I want to define my geometry in millimeters. And then I click on OK. So now that I created this, I also want to give some wall thickness to the pipe. So I can either use the offset, or I can create another concentric circle. So in this case, I'm going to click on this and just offset slightly. It doesn't matter how thick is the wall, since we are going to solve the problem in the fluid only. So I generate the pipe wall this way. And for auxiliary purposes, I'm going to create one more similar structure just here in the middle. So I need the smaller circle for the smaller pipe, and it's going to have 25 millimeters. And I need some kind of wall here as well. So this is good enough. Now what happens when I switch from the sketching mode to the 3D mode is that SpaceClaim automatically turns the sketch into a surface. If you look at the structure on the left-hand side, you will see the surface now instead of the sketch. So this makes it easier to convert this surface into a 3D object. What I will do here is I will just delete the components of that surface that I don't need. So I can delete this, and I can delete this as well. And I will use this to create my entire geometry. So from here, I will first move this slightly away from the plane that I generated. So I'm going to say move. I will take about 400. And create an elbow. The way to do that is select this surface here. I will select the pull operation, and I want to rotate this. Now, in order to rotate this, I will need the axis of rotation. So let me go back to the sketch and generate one. So in order to go back to the sketching mode, all I have to do is click on this surface that I want, click on the plane. It will insert itself onto the surface, and then I can click on this icon here so I can look straight into the plane. I need to add an auxiliary axis, and the way to do that is to click here, and I'll let the tangent touch the outer surface of this outer circle and generate the auxiliary axis right here. And then I want to move the auxiliary axis by about 100 millimeters away. So again, I can press the space bar, type 100, and then move it here. Now I have enough of the information that I need in order to generate the 3D elbow. So I can click on select. I will remove the mid surface. I will select this annular region and then use the pull operation. Pull typically extrudes surfaces in different direction. It can also rotate them in order to generate the 3D bodies. So if I turn the rotation on, it will ask me to select the axis to rotate about. And this is the axis that I just created. If you see, it is slightly away from this circle. So I can then just start moving this. And you can see that the elbow is being generated as I move the mouse. Again, I can use the space bar and just specify the angle of the rotation that I want. So I want to use 270. Well, I guess let me do 90 instead. So all I needed is to create an elbow of 90 degrees. And I need this tiny circle here, tiny annular region, in order to generate the extra pipe. The main pipe can just now be extruded. So first, I'm going to go back to the pull menu, select one of the faces, and just make a straight pull. And let's take 400 millimeters. So I got my pipe extension. I'm going to move this out of the way. So I'll select it here. Use the move operation, and I can move this quite arbitrarily. I don't have to be very precise. I can move it over here. I can now generate the second leg of the pipe. Select pull. Move by 400 actually. And as you can imagine, I can do something similar to this annular region to create a small pipe. So I have this mixing elbow. You may have seen it before, and it's an ideal conduit to study the mixing of different liquids as they come into the same space. So there's another interesting and really nice feature of SpaceClaim which allows me to pull this object precisely to a surface that I designate. So in this particular case, I want to pull this up to. This is a feature in the pull operation that allows me to pull precisely up to a surface. So if I here click on this, it pulls it right up to the elbow. So now I have just generated the geometry for my demo. That's all I needed to do. That way you can watch this video later and just follow the steps and do everything by yourself. So now that we have the geometry, and by the way, if you have a CAD model, you don't need to do any of that. You can just import the CAD model in SpaceClaim and that's all. Once you have the CAD model, the preparation for meshing is quite rudimentary. There's very minimal amount of operations that you need to do. I want to specify some inlets and outlets. And the reason is that I want to define the capping interfaces in Fluent in order to be able to generate the flow domain. So here, I have an inlet on this side. This is going to be my inlet. And the way to do that is to turn on the groups, select the surface, select create group, and rename this group to something plausible. So I can call this in dash large. I really created the label that I associated with this particular surface. That's all I did here. Then I can create another similar label by creating group, and then I call this in dash small. So I have two different labels now. And finally, I need outlet. So I will call this out. For the purpose of generality, there is one additional step that you need to make if you have multiple objects. Imagine if these objects were split together in your CAD model. And in fact, we can kind of reproduce that situation by splitting them here by using the plane. If I select this edge loop over here, and I insert the plane, and another edge loop over here, and insert the plane as well, I can use split body operation and then split these two into three different sections. So I would select the body that I want to split, and I would select the plane that I want to use as a splitting tool, and that's it. I have two different bodies. And I can use this plane as well. So similarly, if I turn on split body, select this object, and click on the plane, I have now generated three different solids. If you have a complex CAD model with multiple parts that are adjacent to each other, that have surfaces that are overlapping, then before importing this into Fluent, you need to make sure that these objects are sharing their topology, meaning that all of the overlapping surfaces that are adjacent to each other are fused together into a single surface. The purpose of doing this is to be able to create a conformal mesh. You want the meshing regions that belong to these different adjacent objects to share the nodes between them in order to solve this more efficiently. So I kind of split this in order to show you how to do that. Let's use different coloring here. Just for the sake of clarity, I can select randomize colors. So I have, let me do that again, randomize. So I have three different objects that are adjacent to each other, and I want to share the topology between them. Let me remove the curves because I don't need them. And the way to do that is to click on Workbench, select all of the objects, and select Share. SpaceClaim identifies the regions where these surfaces are in contact. We have two such regions, and once I do this, it shares the surface in between. So instead of having two identical overlapping surfaces, we have one single surface that consists of the two surfaces fused together. And you will see that there is a pink stripe in this design symbol saying that the topology between these different objects is shared once you complete this operation. So we have the essentials. We have the shared topology, and we have the name selections in the regions that we want to use in the meshing portion of Fluent. So now all I need to do is save this, and I'm going to save the session as mixing elbow. I can reuse this name. That's all I needed to do for pre-processing. And as I said, if I had the geometry from a different tool, all I would need to do is share the topology and create the name selections. In the next step, we are going to bring Fluent. And in fact, let me show you the full process. So you can find Fluent either from the installation directory In this case, we are looking at Ansys 19.2. You can navigate to Fluent. Here is Fluent 19.2, or alternatively, you could just type Fluent here and then click on the icon. This is the Fluent launching window. We want to start Fluent in the meshing mode in order to pre-process our geometry. And here we select one core for the meshing algorithm and four cores for the Fluent solver. We also have to specify the directory where our geometry file is located. This is our working directory. Once we do that, we click on OK. And if you guys had a chance to look at the previous version of Fluent Meshing, you would see this classical tree with different operations. All of these features are still there. What is new is the new workflow tab. When I turn on the watertight geometry workflow, I see a guided set of operations that are placed in the logical order, starting from importing geometry, sizing the surface mesh, generating the surface mesh, specifying whether fluids are going to be meshed only or both fluids and solids, extracting the flow domain from the surface mesh, and then generating the full 3D mesh. So all of this is the new guided task-based workflow. Naturally, we are going to start from importing geometry. Once we generate the volume mesh, we will seamlessly switch to the solver version of the GUI, set up the problem like we would normally do, solve and post-process. All right. So I have this geometry imported. I have three different parts, as I showed before. We can see the different handles here to select different objects in the geometry. You could select the individual nodes, edges, faces, or the entire cell zones. And here you can expand the geometry to fill the window. You can pan, zoom, rotate, and so on and so forth. Just normal operations types that you're used to. Here we can also insert a clipping plane, which splits this object in half, so we can examine the internal parts. We can change the direction of the clipping plane as well, flip it to the other side, and perform the operations to just kind of see what this object consists of. Once we import the geometry, we need to add the local sizing. And here, this sizing is scoped to the three openings that I labeled in SpaceClaim. So I want to select all three of them. I will call this openings and specify the size of 5 millimeters. Of course, sizing is dependent on how accurate you want to be, and it will be different for different types of meshes and different types of fluid flow problems. But for the demo here, I just want to use 5 millimeters, which gives me about 20 elements across the diameter, which is sufficient enough to solve this flow without excessive expenditure of time. So I'll click on Add Sizing. And you can see that every time I complete the operation, I have a green check mark next to the operation that was completed. If I had a little volume that overlaps this region, I can use that volume to size everything that is within that volume. That's called body of influence type of sizing. But I don't need to use that just now. So once I complete my sizing, I want to create the surface mesh. And when I click on surface mesh, you can see these rectangular or cubic regions The size of each cube is proportional to the default sizing that I see here, which is 17.9 millimeters. As I change this value, I want to use 8 millimeters in this case. You see that the cube changes in size as well. So this is a global sizing. It will ignore the local sizings that you specified, but it will give you a pretty good idea about what your surface mesh is going to look like. So you can observe it even before you generate the mesh. So this looks right, and I will use the default global settings. I want to use curvature and proximity. This is very similar to the workbench meshing options. We can use either curvature, proximity, or both, and I will use the curvature and proximity. Keep the default curvature normal angle and select about 3 cells per gap, which is consistent with our best practices for meshing. So now I want to create the surface mesh. And you can observe the surface mesh as it's completed. So we see that the sizing is slightly finer in the region around the smaller tube based on the geometry. And you can see that we have refinements here because I specified 5 millimeters in the capping regions, and I specify 8 millimeters everywhere else. I can insert the clipping plane again and just examine the mesh and make sure that the distribution is the way I envisioned. Because I split this pipe into 3 different objects, you can see that the sizing is slightly finer here. If I wanted this to be uniform, I could just create the label or name selection for this entire pipe wall and then specify the uniform sizing on the pipe wall. The next step is to give some rudimentary description of the geometry. So here, I need to specify whether the geometry consists only of solid regions or combination of solid and fluid, or combination of solids, fluids, and voids. So I'll select the option number 3 because I want to extract the fluid region from the void. Will you cap openings? Yes, I will. So I'll select yes here. And I leave the third question as a default. So I don't need to change any types of boundary conditions just yet. So I'm going to click on this button to confirm that my geometry is sufficiently described. The next step is to define the capping regions. You can see where it's useful to have some labels. See, all of these are the regions that we want to use in order to create the caps. If I did not create these labels, I could have still used the zones. But we have tons of different zones that meshing generated by generating the surface mesh. And it's definitely much easier to get around here among the labels, where we just have 3 different names. So I want to generate a cap where inlet large is, and I'll just call this inlet dash LRG. And here I can specify the type of the boundary condition that I want to place there. And this is going to be velocity inlet. And I click on enclose fluid region. You can see that immediately as I do that, the new cap is generated right here. And it is sized based on the sizing requirements that I had. Similarly, I can generate the cap on the inlet small. So I call it inlet dash S and L. Still velocity inlet. And then out is going to be outlet. And I'll call it pressure outlet. Now I have all of the 3 caps. Next, I want to update the boundaries, and I just want to check whether this is all correct. So in-large and in-small are the labels that were made on the pipe walls. And Fluent Meshing correctly identified that this is a wall-type boundary condition. This new inlet LRG and inlet SML, they are specified by me as velocity inlets. The out is the wall and the outlet is the pressure outlet boundary condition. So I want to update the boundaries. Finally, Fluent identifies correctly that I have one Fluent region. I will confirm that. And here, I could just click on Update Regions. So this is my fluid region, Fluid 1. I'll call it Fluid. And click on Update. The final step is to generate the volume mesh. So I will create some prismatic layers next to the wall. I want to use 5 layers. I will use the transition ratio and growth rate by the default. And I will use the smooth transition because this is the method that gives a very good distribution of the prism layers without compromising the mesh quality. And then for the type of mesh, I have several different options here. I can select polyhedra, tetrahedral mesh, hex core. All of these were available before. But I want to use the new Mosaic Mesh. So I will select the poly hex core, which will use the poly elements in order to create a transition between the prism elements near the wall and the hex core elements in the center of this volume. So poly hex core is the method of choice here. And I will decide not to mesh the solid region. All I need is the fluid region. So I will select Create Volume Mesh. And here's the full flow domain. I think I somehow omitted the extra pipe. So let me... I think for the demo purposes, I will just use this mesh and complete the demonstration. So you can see that we have a very good distribution of the poly and hex core elements throughout the flow domain. And we have a high quality, which is 0.25, while the skewness is only 0.74. The maximum skewness allowed would be about 0.95, and the minimum orthogonal quality would be about 0.1. So we have much better characteristics of the mesh than minimum allowed based on our best practices. So now I can switch to the solution. I can display the mesh. And here in the new Fluent interface, we can list these objects either by the name or by the surface type. So we have inlet, outlet, and the wall, which are the regions that we want to display. And let's set up the problem. First, you would normally want to check the mesh. This allows you to check the mesh integrity and make sure that the mesh is valid. The second operation allows you to check the quality, and this is consistent with what I got from Fluent Meshing. The next step is to set up the physics. I want to solve this as a steady pressure-based problem. I will turn on the energy equation, and I will turn on the viscous flow. So for the viscous flow, I want to use K omega with, I want to use K epsilon realizable with enhanced wall treatment. This will give me an accurate solution of heat transfer at the walls. So I click on OK here. And I also want to change the fluid from the default air to liquid water. So in order to do that, I need to select the Fluent database and then scroll down to water liquid. Click on copy and close. And what I need to do is in the cell zone, I want to change the default fluid from air to water. So what is left is to specify the boundary conditions. Imagine that you could have various different boundaries here. And you could have hundreds of different surfaces. In order to very easily find the boundary conditions, there are a couple of options that we have. One is click on the boundary conditions and then group by either name or the zone type. If I group them by the zone type, I can see that I have one inlet and I have one outlet. Now, I can also type inlets in the top. And this brings me to the velocity inlet that I defined. I can then specify the velocity magnitude, let's say 0.9 meters per second. I can specify the temperature, and if I don't like kelvins, I can go back and change the units. So I could decide I want Celsius instead. I can scroll down, select temperature, and specify Celsius. Then I can go back to my boundary conditions and specify this as 30 Celsius. Then at the outlet, I want to keep the default constant 0 gauge pressure and select the backflow total temperature of 25 Celsius. And once I complete this, I can specify the solver that I want to use, and for the purpose of this exercise I will just use the default simple, which is a segregated CFD solver based on the pressure. Controls can help speed up the convergence, and the default options are just correct in this particular case. I want to define some monitor quantities. For example, since I specified the velocity at the inlet, I want to monitor the pressure at the inlet. So I can do area weighted average, pressure at inlet, and I could report this as a file, plot, print to console. And then I also want to monitor the temperature at the outlet. So I also want to create a surface report, area weighted average of temperature at the outlet. Again, I can print to file, plot, or print to console. And that's all I needed to do. I can now initialize the problem, generate the initial distribution based on the values at the boundaries that I specified earlier, and solve for 200 iterations. So this shows me the residuals and how they change with the number of iterations. And this plot shows me the area weighted average of the pressure at the outlet. I can see that it converges very well. And I also have the area weighted average of the temperature at the outlet. Now, instead of waiting for this to converge, let me skip to the solve problem. And in this particular case, I actually have the small inlet that I had generated earlier on a polyhex core mesh. So I want to do some post-processing just to give you the idea of what you can look for. In the post-processing menu, we want to start by checking the fluxes. And I want to check the mass flow rate here. So I will select all of the surfaces that are not the internal region and then compute the mass flow rate. I have large and the small inlet and the outlet, and I can see the mass flow rate values of the flow coming into the flow domain and leaving the flow domain. The net result is gives me the idea about the magnitude of the global error that I just made. And this global error is on the order of 10 to the minus 6, where my other quantities are on the order of 10 to the 1. So I can see that I really do preserve the mass here really well. I can also click on the total heat transfer rate and then compute this over the surfaces that I selected. And again, I can see that my net result is much smaller in magnitude compared to the rates that enter or leave the flow domain. So again, since the net result is several orders of magnitude smaller, I can see that I have conserved this problem really well. So another post-processing detail is I can create different contours. I can first generate a surface that cuts through the middle of the pipe, and the way to do that is to create the surface of constant mesh. I can say that the z coordinate is equal to 0, and then create. So this allows me to generate the plot of the temperature on the mid-plane. So I'll create temperature on z coordinate. And you can see qualitatively how this fluid is going to mix. We have a cold flow from the inlet, hot fluid coming from the outlet, and they are mixing in the outlet region over here. For visualization purposes, I can also plot the mesh. So if I say new mesh and then plot the walls only, I can select the wall based on the surface type and just plot the faces, choose the manual color and select light blue. This just shows me the wall plot. And then I can also generate the plot of the streamlines. So if I click on path lines and then select new, I can start the path lines from the inlets. I'll specify some coarsening here and generate the path lines. I want to color the path lines by temperature as well. So here you can see how you can color the path lines by different variables. And then I click Save Display. So that lets me evaluate both the flow and the temperature distributions. I can observe any recirculation regions, any vortices, any passive corners that develop, and observe both of them together with the temperature distribution. Now, a powerful feature in the new Fluent version is that I have this Scene button over here, which I can use in order to plot all these features together. So I had a contour plot that I showed on the mid-plane. I had the wall that I plotted as a form of the mesh. I can now change the transparency and plot it as a transparent wall, and I can plot the path lines all together. So that gives me a much better picture of the flow in this domain. I know it's kind of a rudimentary example, but the goal was really to show all the features together and how you can generate this by using one single window, one single graphic user interface. To get back to the slides, we have generated a lot of tutorials in the course of development of this graphic user interface and other features that I presented today. All of them are available on the Ansys portal. You can reach the Ansys portal by using this URL, support.ansys.com. And to reach the YouTube videos, you can apply the filters on the left-hand side. Set the version to 19.2 and set the product to Fluent, to product equal to Fluent. And then you will get the listing of all of the YouTube videos. So to summarize, I gave a short introduction to CFD. I described what the method is, how it can be used, and showed the most common application. I spoke about the Fluent new experience with the new workflow, which is entirely task-based and happens in one single window. I spoke about the new Mosaic Mesh, which comprises from polyhedral and hex elements, which are distributed in order to provide the highest quality mesh for an arbitrary watertight geometry. And I spoke about new features that have been recently introduced in Fluent Well, that's all. Thank you very much. So I assume we're offline.
Sorry about that.
Are we offline?
Hey, we still live? Yep. All right. Hey, big hand for Zoran if we didn't already. Take you. All right, so thanks for joining, and if you missed the first part of this webinar, just rewind to the beginning and take a look at the resource section. If you liked what you saw here and you want to learn more, see more examples, highly recommend the Cornell MOOC and the other resources at the beginning. Thanks, and have a wonderful evening. I hope we see you again next week. All right, in the room, you guys have any questions for us?
Yeah, now I can answer any questions. I think we had some limitations during the live.